Somewhere in the dark of our galaxy spins one of the fastest, densest, and most dangerous objects known to science, a pulsar called J09520607. It rotates 707 times every second. That's faster than the blades of a jet turbine or the spin of a blender, and it does so while holding nearly 2.5 times the mass of our sun. If somehow this star were brought down to Earth, it would fit comfortably within the boundaries of New York City. Hit subscribe and join us as we uncover the mysteries of space. Welcome back to Beyond the Stars. Pulsars are what remain when massive stars die. They are the collapsed cores left behind after a supernova, a cosmic explosion so powerful it can briefly outshine an entire galaxy. What's left is a sphere only about 20 kilometers across, yet so heavy that a teaspoon of its material would weigh billions of tons. That density is almost impossible to imagine. It's matter crushed to the point where atoms no longer exist, where protons and electrons have fused into neutrons, forming one gigantic atomic nucleus. If you dropped a pebble onto the surface of a neutron star, the impact would release more energy than 1,000 nuclear bombs. Gravity there is so strong that a spaceship would need to travel at half the speed of light just to escape. Compared to that, the pull of the sun feels like nothing. And yet, this terrifying gravity is the only thing keeping the star from collapsing further into a black hole. But the story of J09520607 isn't only about gravity. It's about motion, hunger, and survival. This pulsar spins so fast because it has a companion, a dying white dwarf star. Over time, the white dwarf has drifted too close, and the pulsar's immense gravity has begun tearing it apart. Streams of gas spiral toward the neutron star, forming a glowing disk of plasma. As the pulsar devours its neighbor, it absorbs the star's energy and angular momentum, spinning faster and faster, like a figure skater pulling in their arms. These systems are called black widow pulsars, named after the spiders that consume their mates. The white dwarf grows smaller and dimmer as its mass is stripped away, while the pulsar grows heavier and more dangerous. But there's a limit to how massive a neutron star can become. If J09520607 gains even a fraction more mass, it will no longer be able to support its own weight. Its collapse would be instant and absolute. It would become as an influx of black feet consumed by fate. To understand how something so small can be so heavy, we need to return to the moment of its birth. When a massive star, perhaps 8 or 10 times the mass of the sun, runs out of fuel, it can no longer produce the nuclear reactions that counteract gravity. The star's core collapses in a fraction of a second. Protons and electrons are forced together into neutrons, and the outer layers rebound violently, creating a supernova. What remains is a neutron star, the densest form of matter in the universe that can still resist total collapse. A newborn neutron star is unimaginably hot, with surface temperatures reaching 10 million degrees. Its crust is thought to be solid iron, harder than any material on Earth, and beneath it lies a fluid of superdense neutrons that behave more like a liquid than a solid. Scientists believe that even deeper within, under pressure billions of times greater than anything we can reproduce, matter might dissolve into its fundamental components, quarks and gluons, creating a soup of subatomic particles unlike anything else in the universe. These stars are also among the most magnetic objects known. Their fields can be 1 trillion times stronger than Earth's. In some rare cases, that magnetic intensity becomes extreme. These are magnetars. Only a few dozen have been discovered, but they are the most violent stars in existence. When the stress inside a magnetar's crust becomes too great, it cracks, releasing bursts of X-rays and gamma rays so powerful they can be detected across the galaxy. A single outburst from a nearby magnetar could damage Earth's ozone layer or disrupt satellites and power grids. Fortunately, the closest one is thousands of light years away. Ordinary pulsars, though less extreme, are still awe-inspiring. They emit narrow beams of radiation from their magnetic poles. As the star spins, these beams sweep across space, flashing with perfect regularity, like a cosmic lighthouse. Some pulsars are so precise that they rival atomic clocks in accuracy. The first one was discovered in 1967 when astronomers picked up radio signals repeating with astonishing precision, so steady they first suspected an alien source. Pulsar's spin gradually slows down over time, but if it has a companion star, that process can reverse. As it draws in material from its partner, the pulsar recycles itself, spinning faster and faster. These are the millisecond pulsars, and J09520607 is the fastest of them all. Each rotation hurls the surface of the star through space at a quarter of the speed of light. The magnetic field rips electrons and ions from its crust, accelerating them into space as radiation. The energy released each second dwarfs everything humanity has ever produced. It's not just a star, it's an engine of pure physics, a beacon marking the boundary between matter and the abyss. But the pulsar's fate is sealed. As it feeds on its white dwarf companion, it creeps closer to the threshold where no force can save it. When it reaches about 2.5 solar masses, gravity will win. The neutron star will collapse into a black hole, and all that remains of its once brilliant beams will vanish into darkness. Not all neutron stars are so deadly. Some shine gently in X-rays, cooling slowly over millions of years. Others drift through space quietly, invisible to most telescopes. But all of them are relics of death and creation, the final heartbeat of a massive star. Among the most famous is the Vela pulsar. It spins 11 times per second and sends out beams of gamma rays so intense they illuminate clouds of gas spanning a light year. NASA has turned its radio signals into sound, a steady rhythm like a cosmic heartbeat, a reminder that even dead stars can still sing. Pulsars and magnetars are not just curiosities, they're tools for science. Because their signals are so precise, astronomers use them to test the laws of physics, to measure the fabric of space-time, and even to detect ripples caused by gravitational waves. Networks of pulsars across the sky act like a galactic observatory, helping us study the invisible dance of massive objects, merging black holes and colliding neutron stars. And yet, amid all this destruction, there are hints of creation. In 1992, astronomers discovered the first planets outside our solar system, orbiting not a normal star, but a pulsar. PSRB 1257+12 has 3 rocky worlds, each several times more massive than Earth. These planets likely formed from the debris left after the supernova, proof that even in death, stars can give birth to new worlds. It's unlikely that life could survive in such a place. The radiation alone would sterilize any surface, but the fact that planets can exist there at all is a triumph of nature's resilience. While pulsars and neutron stars fascinate us today, the early universe may have produced even stranger objects, quasi-stars. These theoretical giants may have existed only a few 100 million years after the Big Bang. They were enormous, thousands of times more massive than our sun, powered not just by fusion but by black holes at their cores. The black hole inside would feed on the star's matter, while radiation from the infalling gas kept the outer layers from collapsing. Such a star could shine brighter than a small galaxy, living only a few million years before collapsing entirely into a supermassive black hole. If quasi-stars really existed, they might explain how the universe's first galaxies grew such massive black holes so quickly. They may even have seeded the cosmic structures we see today. Though none survived, their legacy could live on in the gigantic black holes that anchor galaxies like our own Milky Way. Some scientists have wondered if smaller versions of these early black holes, so-called primordial black holes, might still drift through space, invisible but influential. If one were ever trapped inside a star, it could slowly consume it from within, turning it into a Hawking star. Such stars would appear cooler and dimmer than normal, and a few candidates have already been spotted. It's even possible that some of the mysterious dark matter surrounding galaxies could be made of countless ancient black holes, relics from the dawn of time. Even our own sun could, in theory, hide a tiny one without us noticing. It's unlikely, but not impossible. The universe is full of surprises, and every discovery pushes the limits of what we think we know. Neutron stars, pulsars, magnetars, and black holes all are part of a single cosmic story, the cycle of birth, death, and transformation. They explode, scatter elements that form new stars and planets, and leave behind the most extreme remnants in existence. From their ashes come the iron in our blood, the gold in our jewelry, the calcium in our bones. Every atom of our bodies was forged in stars that lived and died billions of years ago. So, when we look at a pulsar's flashing light, even one as distant as J09520607, we're seeing the memory of that process, the echo of stellar death that made our own existence possible. It's a reminder that the universe is not just a place of destruction, but of renewal. Every collapse gives rise to something new. Every ending begins another story. And somewhere, out there, even now, another massive star is nearing its final breath. Its core will collapse, its outer layers will erupt into a supernova, and in its place, a new neutron star will be born, another cosmic heartbeat, another beacon in the dark. Liked this journey through the stars? Hit subscribe and don't miss what's next.